I'm Joe Feighan, and right now I'm chemistry professor at Cabrini College. If I'm supposed to give you information on how I started in science, it's right after the war on the GI Bill. When it came to picking a major, it came down to where will I be sure I'll find a job. So I wanted to stay in history, loved history, read in history, and only took chemistry sort of an insurance. If I couldn't get a job teaching chemistry, I was sure I'd get a job in the lab. I mean, it's one of the poorest excuses, I'm sure, for being a chem major. Roughly at St. Joe's, you took a standard program, 4 years of chemistry, but double courses in your senior year, specialized courses in your senior year. And at that time, Dr. Bray was the P-Chem teacher, and he picked a couple of us to work on his own research, which at that time was consecutive reactions with alcohol, and wowed us with the consecutive type equations for the mechanism, for the rates. When I got almost to the end of that, let's say a month or so before graduation, and I had talked about graduate school, Bray sent me down to see Dr. Crieger at Penn, who had been his thesis director. And when you first meet Crieger, you're looking for the fullback of the football team. He was 6'3" or 4", weighed over 200 pounds, looked the part, had the physical build to be a football fullback. And then when you sit down and talk to him, he's the nicest and gentlest guy you've ever met. Would let you lead all the way. When it comes down to, do you want to come here right away, it's like, I have a problem that you'll be interested in. How about if you think about coming here in September? And when I brought up the idea of expenses, he said, don't worry, I'll take care of a scholarship. So from then on, I was hooked. And when I first got down there and started under a regular graduate level lab course with him, we set up a carbon monoxide oxidation problem over carbon. And it became the weirdest thing in the lab, in that we used a carbon filament incandescent bulb for the catalyst. Had the glass blower punch a hole in the bulb and put a tube on the end, and we hooked that to the top of the apparatus. So anytime you were working, anybody look in the lab and you see the light bulb on. Then that eventually became, the data from that eventually became the beginnings of the actual PhD thesis research. Now, for the thesis research, it turned out to be work on single crystal faces. This is where you can best demonstrate Crieger's background, in that he had probably 6 people working for him at the time, PhD research. And of the 6, everyone was on a completely different idea. One would be doing free radical work, one's doing pyrolysis, one's doing standard decomposition reactions or catalyst preparation. In my case, we worked with single crystal stuff. He was amazing in that he would pick up any new technique or any new idea, look at it in depth, and maybe try to use it. I remember first him talking about what he referred to as emanations, which was an old publication. I guess now we look at it as, we think of it now as radon gas, I guess. But at that time, he referred to it that way. He looked at some of the Russian stuff where they were trying to see about catalysts that would work better if there were radioactivity incorporated in the catalyst to decay particles, maybe change in catalytic effect. Some of Valentin's original work, I think. With me, we started out with the idea of, do single crystal faces have preferential absorption characteristics? And we first tried to make our own single crystals by taking the spheres that Blockley made at Virginia and X-ray orienting them, and then tried to polish them down. And this amounted to mounting the sphere with on a tail with a certain orientation against a grinding wheel. And we ground the thing down little by little over a period of hours. And you're grinding down preferentially exposing that face. it turned out hours didn't work, it turned out to be days or weeks. And I can remember many times falling asleep watching the damn wheel go around. And that if it would snag and stop, you could ruin your crystal face. It would start to etch very quickly because it dipped in and out of the nitric acid bath. And 2 or 3 times he's come into the lab and found me sound asleep. But we used those for a while, and then we cut behind the faces to get a 100, 111, and 110 face. And then did the same kind of work with nickel, or did the same kind of catalyst run with nickel, in which case we bought those as already prepared single faces from either Guathmy or Lighthizer, who was one of the students. And you could get them then about the size of a little bit smaller than a penny. And each one that you bought then ran around $200, and presented a single orientation. For the run, we would react carbon monoxide and oxygen over the crystals and make carbon dioxide gas, and then try and see if absorption took place before or during or after the reaction itself. Now, to do that, you use radioactive carbon monoxide, radioactive carbon dioxide, and with various techniques tried to count on the surface, actually in the vacuum system, with homemade Geiger tubes. You actually built your Geiger tubes, built the windows for them from mica, and you might end up blowing 3 windows before you got a single one. If you got good with this, with the glue and the mica, you might make 1 good window with every 5th or 6th try. So it's sort of like a gold mine. You banked your spare windows. What came out of the research eventually was a ideal mechanism for the reaction with minimal absorption on the surface. Now, maybe something less than, we were able to demonstrate that carbon monoxide or carbon dioxide absorption didn't take place on any of the crystal faces, at least down to 0.1% of surface coverage. At the time, Guathmy, I think, was the only one doing any kind of single crystal work. This would be about 1952, 53, 54. And they were doing oxidations of the crystal itself rather than catalytic reactions on the surface. Somewhere later, by 56 or so, Farnsworth was carrying out some single crystal studies, I think using either an electron diffraction study method or maybe electron microscope?
Low energy electron diffraction.
Okay. But as far as the actual reactions, I think we were pretty close to the first that had done some of this. During it, Crieger was extremely supportive. I mean, we'd have times in the original studies where you'd run the reaction and then spend hours taking 5-minute counts as you rotated the spherical crystal around with maybe an unknown orientation facing the Geiger counter. And you might take a 5-minute count over a 10, 12-hour day. Take a 5-minute count, check a background, take another 5-minute count, rearrange the alignment of the crystal and keep this up. And there was never a time when he wasn't available for help. The amazing part of him, he was the best teacher I've ever had, one of the gentlest persons I've ever met. Never once heard him raise his voice, never once heard him use off-color language. If you wanted him, generally just made an arrangement to meet him for coffee. And almost all his advising was done in the coffee lounge at the university. But as far as impact on chemistry, he was the real reason I stayed in catalysis. And then since that time, I've had 2 or 3 students who would come in, they'd get a catalysis problem to do, and some of them went on the same way.
Well, now, you had a job at least part-time while you were at Penn, if I remember.
Yeah, I ended up, I was teaching full-time at St. Joe's in the chemistry department. So the lab work would be done after 4 o'clock in the afternoon. And you'd end up going down to 4 o'clock in the afternoon, staying until midnight maybe. The biggest nuisance value of it was that the apparatus, the vacuum apparatus, obviously would be better if it was continually pumped. So it meant you had to have liquid air in the thing, in the cold traps. At that time, our liquid air containers were 15 liters. So you'd have 2 of them for the research. Penn made their own liquid air. So you'd have to go every Monday, pick up 2 15-liter cans of liquid air, drag them down the street to your lab, struggle with them down the steps and into the basement, and then add liquid air. The apparatus at that time would only stay cold about 20 hours. So no matter what happened, 7 days a week, you had to make sure that your maximum time away from the lab was 20 hours. This included Christmas Eve or Christmas. 2 or 3 times, you'd be taking a stolen liquid air container down 34th Street, and they would smoke, obviously, as they're splashing back and forth and evaporating. 2 or 3 times, I'd be stopped by the police to see what you were stealing, what was going on, why the thing was smoking. And you'd have a hard time convincing some Philadelphia cop who had made it through 8th grade that this was scientific research. It's an amazing thing as far as research. Had there not been a guy who made the liquid air, I'd have probably not finished. Had there not been top-notch machinists in Penn's engineering department, you'd have probably never been able to get the apparatus to hold a vacuum with O-rings. It's one of the early use of O-rings for movement through a vacuum system. The shop guys, the same way. The help you would get from your own students, your own undergraduate students, would be like, we won't look for you to help us with any tutoring or homework problems or anything, since we know you're going to do graduate research at 4 in the end. They'd always make sure they could time things to catch you earlier. The priest who was the head of the department at the time, Father Malloy, was tremendously supportive. But all of these things contribute, and without that you wouldn't stay. You would never finish. After I finished and graduated, I went to Oak Ridge and worked on some irradiation studies, and met Emmett down there, Paul Emmett, and again, he's extremely helpful. A guy who wouldn't mind sitting and talking to you, wouldn't mind suggesting things. Ellison Taylor was another one down at Oak Ridge, and he was in catalysis. He was at that time head of the chemistry division, and had worked in catalysis and gone to Oak Ridge at the beginning of the war. And they were like tremendously pleased to get a catalysis man to come down there. After that, back at St. Joe's in master's degree research, I was able to continue the lab work, the single crystal work for a while with 2 or 3 different graduate students. Later on, I did some work on iodine exchange reactions, catalyzed with aluminum oxide catalyst. And in those, we try to work for mechanisms for the iodine going on, which catalyst it went to, which carbon it went to in, let's say, isopropyl iodide or propyl iodide, butyl iodide, which of the carbons the incoming iodine attached to. And we used iodine label and carbon-14 label for some of that work. I remember one time getting a phone call from Crieger to show the kind of personality he has. He had known about this for a while. He'd gotten a graduate student for PhD work. He called up almost to ask permission, would he have the student work on a gas phase exchange, or would it infringe on my work? It's almost like an unbelievable, it's almost like a pat on the back, but it was just his personality.
Well, if I remember, the carbon-14 work indicated you were forming what would be equivalent to allyl type, where the 2 N carbons became equivalent long before this became a popular.
Yeah, in the in the catalyzed exchange of the iodide with the alkyl iodides, these were done in solution, and they were done with a catalyst in contact with them. If you did it with ethyl iodide, which was the first one we spent tremendous amounts of time on, the iodine could either go on the same carbon that first held iodine, or it could go on the number 2 carbon to that. Well, there's no way to break the mechanism there. When we got to propyl iodide, we were able to demonstrate that the let's call carbon number 1 has iodine on it. By labeling that, and then later on labeling the third carbon down the line, we were able to demonstrate that the attachment came with that third carbon. That you actually had a 3-carbon intermediate, with each of the 2 outside carbons identical, and by an attractive arrangement, the incoming iodide ended up on carbon number 3. And it's a pretty unambiguous result. Now I tried it with butyl, isopropyl, and I think secondary butyl, and we did not get as conclusive a set of results. You got much more variety in those. But the biggest thing I remember about it was Crieger calling up and saying, "Is it all right if I try something different that you haven't done? Would you be upset?" It's like major compliment. The other thing I remember, when I got out of St. Joe's in 1963, students threw a farewell party or dinner, and Crieger came to that, and he ended up as one of the guest speakers. And publicly he comes up with, "Well, this guy sitting here, when he first came in, was like an older boy, and by the time we finish with him, he's a chemist." And he says, "I want him to know now I'm pleased with what he had done." Well, we tangled right after the talk, and I said, "For 5 years I worked here, and you never once said you were pleased." "Oh no, if I'd have told you that, it might have gone to your head." He said, "I want to keep you going as a research chemist. He said, I didn't want you to think you were doing too great." So, I mean, my experiences at Penn were all good ones, and 95% of that is because of Crieger. His impact as a teacher has never left. His impact as a researcher has never left me. But as I mentioned before, he had the ability to pick up on anything new and concoct a problem and maybe carry it through. You done?